All right. To finish off this proof of concept that we're working through of predicting whether or not someone has heart disease, we're going to fulfill the last requirement that our boss asked of us, and that is feature importance. So let's make a little heading here. Feature importance. It'd be beautiful. Now, what is feature importance? Well, feature importance, let's just put a little note to ourselves. Feature importance is another way of asking which features contributed most to the outcomes of the model. And you could also extend it, and how did they contribute? This is useful to know, since we're trying to predict heart disease using a patient's medical characteristics. Which characteristics, for a refresher, we've seen this a few times now, but we'll refresh ourselves. We're using this data here. So, which one of these characteristics of age, sex, CP, all these other ones, cholesterol, phthalac, exang, and if you want a breakdown of what they are, we can revisit our data dictionary up the top. We're looking at here, feature importance. Which one of these contributes, and how do they contribute, or how much do they contribute to predicting the target? So, how would you exactly find it out? Well, finding feature importance is different for each machine learning model. Now, as we saw before with how to tune hyperparameters of a certain model, what you might want to look up, and since we're using logistic regression to calculate all of these metrics, a logistic regression is the model that we found by grid search, by tuning the hyperparameters to get the best results so far. What you might look up is something like this: how to find feature importance using logistic regression. If we go here, a look into feature importance using logistic regression, model-based feature importance, how to find the importance of features of a logistic regression model. If you went through this, you could insert almost any model here, so random forest or KNN classifiers or something like that, and you'd find a bunch of different methods. So what we're going to do again is pretend that we've done our research. Our boss has gone, can you get the feature importance of that model? And we've gone, hold on, I'm not entirely sure what feature importance is. So we've gone away for overnight or for a couple of hours, done our research, got our model and figured out, okay, this is how we find feature importance. Beautiful. So that's what we're going to do here. We've pretended we've done this research, but remember, part of being a machine learning engineer, part of being a data scientist, the most important thing is researching and experimenting. It's built into our framework that we're using. Experiments. That's what we're doing here. We're in the modeling phase, really. That we've created the heading for it, but really we're experimenting. So let's figure it out. Let's find the feature importance for our logistic regression model. I'll put here a little note. One way to find feature importance is to search for, so you can put in here, I'll put it in brackets, model name, feature importance. That's one way to do it. That's what we just saw up in this little search here. That's what you should try out if you're curious to how to find feature importance with whichever model that you're using. So first of all, we're going to fit an instance of logistic regression. We'll create one with the best params. So gc log reg best params. We'll see what that is. Shift and enter. Wonderful. And then we'll go CLF equals logistic regression. We're going to pass it a C value of this long decimal. Here we go. And then we're going to pass it here. Solver liblinear. Beautiful. So we've got our CLF. So we'll instantiate that. That's our classifier. And then we'll go CLF.fit xtrain ytrain. Wonderful. And now, through our research, we've found that there's an attribute to our fitted logistic regression model called CoF, which stands for coefficient. Okay, and the way I kind of remember this for logistic regression is coefficient kind of reminds me of correlation. But let's see what happens. Remember, we found this through our research. We've looked up how to find the feature importance for a logistic regression model, and it's told us if we're using scikit-learn, specifically logistic regression, and if we fit the model, we can call the coef attribute, which gives us the coefficient, right, the value or how each parameter, let's look at our data set again, how each of these independent variables, so the X-train data set, the coefficient contributes to our labels here, or the target labels. Whew. So that was a bit of a mouthful, but what we're going to do is manipulate this coefficient array so that it looks like it makes sense. Because right now it's just a list of numbers, but if you counted them up, they're actually going to be the same length as what's happening here, these amount of columns here. But let's just twist them together. So we're going to match the features to columns. Coefs of features to columns. So this is going to make sense. That's what I'm trying to get at. This will make it make sense. Dict. So feature dict. We're going to create a dictionary and we're going to zip together df.columns. And we're going to list along with clf.coef 0. And let's see. Feature dict. Boom. Look at that. How good is that? So if we go here, we've mapped all of the different variables here to the right column. Let's remind ourselves of what's happening here. df head. So all we've done is we've taken the coef array, right, which is an attribute of our classifier, and we've taken the columns from our data frame, and we've mapped them to each other. So what this is telling us is how much and what way, see, we've got some negative values here, whether it's a negative or positive correlation, how much each of these contribute to predicting the target variable. Whoa, that's a bit of a mouthful then. Another way, visualize feature importance. Actually, I shouldn't have told you that. I should have told you that was a little magic trick that I had. Magician never reveals his secrets. What we're doing is we're visualizing this so we can kind of get an idea of what's going on. So index equals 0, different line. Feature df dot transpose. A lot of transposing plots here, but that's all right. Title equals title. Feature importance. We'll go legend. No, thank you. Whoa, there we go. So, does this make sense? What is happening here? So this, in essence, is how much each feature here contributes to predicting the target variable, whether someone has heart disease or not. You can see that some are negative and some are positive. And now, you might be thinking, we have seen something similar to this, right? Whether one feature is negative and one feature is positive. If it's not coming to you right now, it's okay. It took me a while to connect these two. But if we go right back up here, right back up to our correlation matrix. So this is where I remember for logistic regression, if we want to figure out feature importance, we use coef because correlation matrix, coefficient, kind of the same thing. Kind of, not really, but you get my picture. So we can see here some different values. So if we've got CP equals 0.43, okay, thal-ac equals 0.42, then we got, what else do we have? Xang equals negative 0.44. If we go down here, now we've got the same thing. So we've got CP equals 0.66. Oh, it's a higher number here. And then we got thal-ac, okay, which is 0.02. We got Xang, which is negative 0.6. So now what we're doing is we're doing model-driven exploratory data analysis. These values have come from building a machine learning model which has found patterns in the data, and it's telling us how it contributes, right, or how it correlates to our target variable. That's what we're looking at here. So, what can we do with these values? Well, let's explore them a little bit and just see if they make sense. So we can see that sex is fairly negatively correlated, like it's almost right here at the bottom. If the value is negative, we saw before with the correlation matrix, it means that there's a negative correlation. Okay, when the value for sex increases, the target value decreases because of the negative coefficient. let's look at this, see if this actually reflects the data. So let's go sex, let's compare df.target. What do we say? So, which means as a value for sex increases, the target value decreases because it's negative coefficient. So, value for sex increases. So, as it goes up, the target value decreases. That doesn't really make sense when we look at this. Look, so sex goes up, increases, but so does the target value. Oh, you know what? After looking at this, you can see that the ratio is what we're thinking about here. So as sex goes up, the target value, the ratio decreases. So you can see here, if the sex is 0 for female, there's almost a 3-to-1 ratio here. So 72 divided by 24 is almost 3. We look at that. 72 divided by 3. Oh, exactly 24. So it's a 3-to-1 ratio here. And then as sex increases, the target goes down to about a 1-to-2 ratio. See, there's roughly the 50-50 here. Okay, so that's a negative correlation, which means that sex is strongly negatively, or a negative coefficient, sorry, because we're using the coefficient, coef. We're using coef up here, the coef attribute. Now, let's have a look at a positive one. CP, or maybe slope, because we've already explored CP before. So let's do that, PD cross tab. I'm not actually sure what slope is, so we might have to revisit our data dictionary. And again, this is model-driven exploratory data analysis here, right? We're trying to figure out what's going on using the results from our model and seeing if what our model's learnt holds water. So it's saying here that as slope increases, because it's a positive coefficient, that means that the target should also increase as well. So let's have a look. So slope, we got a value of 0, 1, 2. So as it increases from 0 to 1 to 2, does the number of samples here increase? Well, I think it does, because here we've got slightly more here. We've got slightly more there, or we've got almost double there. But then as it gets really high, we've got basically triple people with heart disease. So let's go back up to the top and see what slope is in our data dictionary. Slope. What we might do is copy this so we can come back down. Copy that. We'll come right back down to where we were. Now let's see if this makes sense, right? We've got a positive correlation according to our model, a positive coefficient. So we'll put here. We'll change that to markdown. Oh, that doesn't look very nice. We'll put these as dot points. Slope. The slope of the peak exercise ST segment. So 0 is unsloping. So better heart rate with exercise. Uncommon. Yeah, that is pretty uncommon. Flat sloping. Minimal change. Typical healthy heart. Okay. Yep. And then 2, signs downsloping. So signs of an unhealthy heart. Ah, okay. That's making sense, right? This correlation here, if you weren't a medical expert, right, but you know a little bit about how things go. If you were to say someone had an unhealthy heart and you were to ask someone, well, you know that they potentially have an unhealthy heart because their slope value is 2. Would you say they're more likely to have heart disease, aka having a value of 1, or not have heart disease? Well, according to our model, it's giving it a positive coefficient to slope. So as the slope value increases, it means the model is more likely to predict a higher value of the target. And what's our higher value of the target? Because we're only predicting 0 or 1, the higher value is 1. Wow, now we could keep going with this, but this is something that you could probably share. What is the importance of having something like this? First of all, you find out more. So if some of the correlations and feature importances here confusing, a subject matter expert may be able to shed some light on the situation. So this is something you might be able to take to one of your partners or one of your colleagues and go, hey, I'm not sure what's actually going on here with chest pain having a positive coefficient. Are you able to help me out? Or 2, you could redirect your efforts. So if some of these features offer more value than others, this may change how you collect data for different problems. So see here, these don't really influence. These ones here, age, cholesterol, stress, these are all really low coefficients here. Now that might influence how you go about collecting data in the future. Maybe finding someone's cholesterol level is really hard to do. if it's not contributing much to the patterns a model is finding, you might scrap that in future data collection. And then again, this is the third point, it's less but better, right? So if some features are offering far more values than others, you could reduce the number of features your model tries to find patterns in, as well as improving these ones. So that's what we just continuation, really point 2 and 3 are kind of the same thing. You could combine these in some way or improve these or just make the ones that are offering the most better. This would not only save you on computation by having a model find patterns across less features, you could still achieve the same performance with using the features that offer the most value. So that's something to keep in mind. All right, so we've fulfilled all of the requirements in our project that our boss was asking for. We got feature importance, we got cross-validation classification metrics, yes. We got a confusion matrix, so many different matrices here, my goodness. We've got a ROC curve, we've got area under the curve, beautiful. I wonder if there's anything we're missing out. Well, let's figure that out in the next video.